is Bohdan Trach. I'm from TU Dresden, and today I will present you Clemmys, the system for secure remote execution in function as a service. And it's a joint work between TU Dresden in Germany and University of Edinburgh. So as you all know, function as a service is the emerging paradigm of cloud computing that promises to both reduce the amount of boilerplate work that developers have to do, and also increase the performance of cloud systems by allowing easy auto-scaling with using the knowledge that is available only to the cloud operators. So let's have a look at have a bird's view on how function as a service system works. So the typical components of function as a service system is a gateway and a controller, and it has some number of worker nodes that executes user functions or lambdas. So there are different architectures. For that, there is another alternative architecture which uses gateway as a load balancer, but we will focus on the first one. So how the system works is typically it has a TLS connection between client and the gateway. Client sends a request, which gets TLS connection gets terminated, and arguments are provided to the function. Controller schedules execution of functions over worker nodes, where user data is processed. So here, an important feature to support is that makes lots of appeal from the way function service works is function chaining. That is, user requests can be forwarded through several functions and processed there without involvement of the client, and then processed request from the client is sent back over the gateway. But is this system really secure? Well, it has the same trust issues as all other cloud systems. That is, it's a low trust environment. That is, both attackers and malicious insiders of cloud provider can leak secrets. So it has several attack directions. So first attack direction is inspecting the network traffic, because the TLS connection is already terminated inside FaaS system. And also, attacker can inspect application memory, because typically the software stack that's running for example, controller or worker nodes, sometimes even gateway, can be rather complicated and easy to exploit in this sense. So there are several, in the end it boils down to the program of secure or trusted computing on untrustworthy nodes. And there are several solutions for this. So for example, there are solutions based on multi-party computations or homomorphic encryption, but those solutions suffer from high performance overhead and low flexibility. So the approach that we will try to use in our work is based on trust execution environment technology called Intel SGX that promises to remove the overhead and to allow arbitrary workloads inside functions. So let's have a look at Intel SGX. As already mentioned, it's a trusted execution technology that adds an enclave abstraction. And enclave is isolated region of memory containing code and data that's subject to several restrictions. So first of all, it's encrypted while in RAM, and contents of enclaves are plain text in CPU caches and registers. It is not accessible from the outside of the enclaves, that is from other enclaves or from untrusted user space and from privileged software. And it provides developer-specified endpoints for entering and exiting enclave. That is, direct calls and jumps into enclave are forbidden, and there are special enter and exit instructions. It also has several restrictions. So physical memory available to enclave is limited to 90 megabytes. And this causes problems that enclave startups with large enclave heaps are very slow. And why this matters? Well, per function overhead of startup is an important metric that is optimized in several papers. So for example, these ATC papers. And it's a big problem for SGX version 1 enclave, because as enclave heap size grows, the enclave startup time grows as well. That is, if you want to have enclaves that can use up to 4 gigabytes of memory, you will have to deal with 35 seconds of startup time, which is unacceptable. And we will show how to tackle this using SGX version 2. And we will also investigate additional optimizations because this is an important topic. So our research statement is how do we enable execution of wide range of functions in an efficient and trustworthy manner in FaaS. So let's have a look at the design of our system. So it is based on Apache Open-Whisk that has built on its architecture, and we run important components of Open-Whisk, those that are strictly necessary, inside Intel SGX enclaves, providing us trustworthy environment for function execution. We show how we design a message format inside function service system to allow efficient execution of functions and also secure function chaining. We optimize function setup using SGX version 2, and we describe how the key management is done and deployment of functions is done. So gateway, the goal for our gateway is implemented based on Nginx plugin. And for trust execution environments, we use a Scone framework, which allows execution of unmodified POSIX applications inside SGX enclaves. So let's have a look at the basic design of our internal encryption. So one of the first approaches that comes to mind, we could try to run each Open-Whisk component inside SGX enclave. But this is all because of EPC paging, because lots of Open-Whisk components are implemented in Java, Scala, Python. Therefore, they hit this 90 megabytes EPC size region, causing paging and inefficient execution. So clearly, we want to run the Open-Whisk components outside of the enclave, other than gateway and function. But in this case, we cannot also use TLS, because if attacker can read application memories, then attacker can always leak the secrets for traffic encryption, or just directly read requests from the Open-Whisk components. So our idea here is that we want to separate the metadata that is necessary for controller for management of enclaves, while encrypting only the user data that must stay secrets, for example, arguments or data that is passed to the function. And we will, the further details of the message format are available in the paper. Yes. So also, another important requirement for this message format is that we have to be able to verify the function execution order. Because, for example, if attacker can skip an execution of functions, for example, in a chain for image processing with 3 functions, scale, feature, detect, and report, if attacker can skip execution of one function, then potentially if the function is disclosing some information in plain text, this can be used for leaking the user data. Therefore, we want to be able to enforce the function execution order in a chain. So this is also available in the paper. So we will go into detail with the way we optimize the function startup. So, for example, let's see how enclaves are created with SGX version 1. So in this case, the pages are added until the EPC size is hit, and at that point, they are added only as other pages are paged out. And this causes this linear dependency between enclave size and the startup time. But with SGX version 2, we have a protocol for dynamically adding pages to enclave. And in this case, we can add only parts of enclave to part of enclave pages, and the rest will be added dynamically. So this way, we add only text and data section of enclave at the enclave creation time, and also some small metadata that is necessary for heap allocator. And all the rest of the pages, that is BSS and heap sections, will be handled at runtime. So then, as pages are accessed, they will be dynamically added to enclave. So at this point, we can investigate additional optimization. That is, assuming that the memory accesses are highly local, instead of adding a single page to enclave, we could try doing a so-called batch augmentation, that is batched addition of pages, and add a block of n pages instead of single page. Another optimization that we do is that with SGX version 2, we have a guarantee that enclave pages that are added dynamically are zeroed out, which is not guaranteed for SGX version 1, because then if you add pages, they can have arbitrary content unless they are measured. So in the optimizations that we do is basically that we move zeroing of memory from the memory allocation pass to memory deallocation pass. And here we have assumptions that functions will allocate lots of memory and then exit without freeing it explicitly, which will save some time on zeroing out those pages. So let's have a look at how the system works in general. So here we make use of a alignment system that's a remote attestation service, and it also provides remote configuration and secret management. So it is the way it does remote attestation is very similar to the Intel data center attestation primitives. I'm not sure if you're aware of that, but yeah, the details will be available in separately published paper sometime soon. So what it provides is it provides transparent secret management for SCOAN applications. That is, it allows transparent replacement of application arguments and environment variables inside enclave in a trusted and efficient manner. So what user first does is user has to establish trust in Polyamon, and for this Intel attestation is still used. And after that, a client uploads secret and function chain configurations into Polyamon. Now, after that, client can upload functions as Docker containers or basically in OpenWhisk zip format to the controller. As the functions are invoked, so first of all, Polyamon has to start as a gateway and provide remote attest it and provide it with secrets that are passed by the client to Polyamon. And at that point, the client can do a request to gateway. Now, if gateway replies with a certificate that was provided by client to Polyamon, then we know implicitly that that gateway was attested with Polyamon. Thus, it is trusted and secure. Also, in this case, gateway has access to the encryption keys that are necessary for encrypting the message for the functions. So the request is passed to controller. Controller executes, it inspects the plain text metadata that is available after the gateway and passes it to the worker platform, which spawns the function using also plain text metadata from the controller. So what function does, it also establishes connection with Polyamon, gets decryption keys necessary for getting the encrypted data into plain text format, and it after that reads the message, the encrypted part decrypts it and executes. So let's have a look at the evaluation, how the system performs. So first of all, we compare we try to break down the overhead of the system into several components. So first we inspect the overheads from the gateway. And here we compare the response time, changing the number of functions running in parallel on a working node, and the lower the better. So we can see that performance overheads from the gateway are very small. So there are only minor performance overheads from the gateway. So it's 1 to 5%, but you should also keep in mind that the messages that we sent were rather small. Additionally, we try to compare what is the overhead from the function runtimes that we inject into our application that takes care of decrypting the message, verifying the function chain order. So here we also compare response time, also changing the number of functions running on the node. And we can see that there is some overhead for some functions, but not for all. So as a result of our experiments, we saw overhead of up to 25%. So another comparison that we do is to evaluate the impact of optimizations that we did. So here we compare functions running with SGX version 1 and functions running with SGX version 2. Here we compare the speed up, that is higher the better. And we compare several variants of our applications, that is SGX version 2 is SGX version 2 with all optimizations, SGX version 2 with no flashed augmentation, and SGX version 2 without any optimization calls, that is plain SGX version 2. And we normalize the performance by the performance of SGX version 1. So here we see is that in most cases we have a huge speed up from using SGX version 2. But on the other hand, other optimizations provide benefits only in very limited number of cases. That is the functions like BDUP and FaaS that have memory allocation and usage patterns that fits these optimizations. In all other cases, there is no benefit whatsoever. Also, important thing to keep in mind is that these functions were running with rather large heaps, or rather allocated with rather large heaps. This means that they try to, the maximum amount of memory that was available and runtime was 4 gigabytes of memory, but they were not running with using these old heaps, they were running without EPC paging. This was done to simulate the execution of Python functions, which typically execute some amount of memory for garbage collection, but they do not actually touch all of this memory at the runtime. And the thing to keep in mind is that this is not because the functions run so fast, it's more because we allocate a big performance overhead at the startup. So in general, that's the Clemmys systems that we developed. So we achieved the properties that we wanted, that the system is secure, it protects execution of functions with Intel SGX, it is fast, achieves near native performance, and also it's flexible in that it does not restrict the workloads that can be executed inside functions. Thank you for attention.
Thank you. Any questions?
Did you measure the throughput? You showed the overrate for latency.
So for throughput, it was not so good, but the problem is that we had a very tiny node for evaluation because there is only Intel Pentium Silver, basically mobile CPU with 1.5 gigahertz available for the evaluation. We had only one machine of those. So yes, throughput in our experiments was not so good, but this can be improved when we get beefier hardware. Yes?
I noticed that you pass to the workers information that is the parameters are encrypted, but metadata is plain text.
Yes.
Correct? So, but I'm referring specifically to parameters. So, in other words, this also affected. I mean, serverless platforms and notably OpenWhisk are polyglot in the sense that they support functions written in multiple programming languages. But I guess that for this case, didn't you need to go and alter all the runtimes of the different languages to support this encryption?
So there is a rather small wrapper that is implemented using cryptographic libraries for decrypting. That's true, but we can keep it as a native component and embed it into runtimes of each language, so it stays generic. Some amount needs to be adapted, but it's a very small amount of code. Basically, decrypting is a message and checking the function chain order. It's not a big amount of code, up to, 200 lines of C, around 15 lines of Python, not too much work.
Any other questions? So one question for me is regarding the space usage. Did you test how much memory is being used by the different, and basically how many parallel functions you can run before you run out of space on the enclave page cache?
Well, this would be highly function detection dependent, so it would be hard to do a meaningful comparison here. So in general, if FaaS, so the promise of FaaS is that we have almost infinite scalability, and with current SGX restriction, it may mean that cloud provider would have to allocate lots of nodes with Intel SGX for trusted functions. But I guess this would also add some motivation to extend the APC size.
Okay. Let's thank the speaker again.